Okay, well, welcome to the morning session today. And the first talk is by Søren Fournais, angular momentum distribution of electrons in large neutral atoms. So please.
Thank you very much. First, let me start to congratulate Volker. I'm very happy to be here. Thanks to the organizers as well. But Volker has been very instrumental for my education. So when I was a student, somewhere between 25 and 30 years ago, there was something called the TMR network in Europe. That Volker was one of the leading scientists in, and I think I speak for a whole generation of mathematical physicists, that was a great initiative. And I like to look at mathematical physics in Europe now that I can see it's really flourishing, and I think that is to a large extent due to well, the initiative that you and the rest of the TMR PIs did at that point, and I think I speak for a generation to say that we are very grateful. So I think I met you for the first time in one of these meetings, maybe already the first one in Oslo, with the lutefisk. Yeah, and we will not get into details about that here. But I learned a lot from that whole development. I mean, those several years of continuing network, which was very, very good. Thank you very much. So what I will talk about here is joint work with August Bjerg, who was a student in Copenhagen, Peter Hønshaw, who's a postdoc, and Jan Philip Solovey. So the title is Angular Momentum Distribution of Electrons in Large Neutral Atoms. And there's a subtitle here in blue that may or may not be readable. Sorry for the colors. I thought that was pedagogical, but I might have been wrong. Deviation from Madelung's rule. And as I say, I tried to be pedagogical, so that I tried to use some red, which I thought had a good contrast to black. But so if there's something that kind of looks mysterious, but there's what looks like a hole in the transparency, maybe it's because something is written in red there and you cannot see it. So please just ask a question. Okay, so what is a large neutral atom? For me, I will try to be sort of very basic. So most people here would know that, but I take the standard model of an atom, right? We have a kinetic energy for each particle given by the Laplacian. There's a Coulomb attraction from the nucleus, and there's an electron-electron repulsion. And I use the fact that the electrons are fermions. So eigenfunctions have, or the wave functions have to be antisymmetric with respect to change of coordinates, both spin and position coordinates. I think it's better if we turn off the light. And to stress the fact that, I mean, there's n, which is the number of electrons, and there's c, which is the nuclear charge. To stress the fact that I wanted to look at neutral atoms, there's written in red here that n is equal to c, and that n, the number of electrons in my space, is equal to c. And over here, the sum is over all electron coordinates. So up to n, but of course n is equal to c. At this point, it's maybe not sort of crucial whether you can see the red part or not, and I hope it will not be too crucial later on. Okay. Strictly speaking, I've chosen some units here. The h bar is equal to 1, the electric charge is equal to 1, and 2 times the electric mass are equal to 1, so that I have essentially constants equal to 1 everywhere in my operand. So that's a choice of units that I can make. And it's known that for the neutral atom, then a ground state, so an eigenfunction, realizing the lowest point in the spectrum exists. It's possibly not unique, but I will choose one, and my statements will be for independent of the choice that I make. So the ground state is an eigenfunction where the eigenvalue is the lowest point in the spectrum. Of course, the spectrum where the operator is realized on this antisymmetric. And the title large, the word large in the title means that I will study the limit of taking n, which is equal to c, going to infinity. So the atom is always electrically neutral, but that number of electrons equal to the nuclear charge goes to infinity. So that's going to be my asymptotic parameter in order to be able to do some big mathematics. Good. This links to some of the very early work of Volker. There was important work, I think, from 93. I forgot to put in the year here, but it's CMP in 93, called Accuracy of Mean Field Approximations for Atoms and Molecules, which inscribes itself in a development around that time of really understanding the energy of large atoms to high position. And this work we will come. I will show later to what extent it comes into them. Yes. No, I think what you should think about there is that even the dimension of the space here, in some sense, you're working in R3 and you have n electrons. You can think of, these are antisymmetric functions in R3n. So you're working in a huge dimensional space if the number of electrons. But then we take n and c equal, because if not, you would have something physically unreasonable of having, say, enormously many electrons, but a very small nuclear charge. That would actually not bind. Actually, yes. So actually, my statements here, it's easier to write just with n equal to c. If you take n equal to 1 times c plus a lower power of c, then essentially. So I'm being very crude here, but just to give an idea, the main thing here is that n divided by c is roughly 1. And what we are addressing here is the fact that somehow chemistry textbooks include rules for how you fill in electrons in the shells of an atom. Now, if you are a mathematician like me, well, somehow these shells don't really make sense, right? We have a completely interacting picture here, and so even the definition of shells is unclear. But in chemistry, they know what they're talking about, and they want to fill in electrons, and that gives us the periodic system of elements. And they have what's called the Madelung rule that tells you how that works. And in some sense, this work tries to understand whether this Madelung rule can be understood as something which is deeply systematic for large atoms that would work even if, the reason why the periodic system is not bigger than it is has to do with nuclear physics. It doesn't have to do with the Schrödinger model that I just broke down, where the nucleus is just taken at the point. So you could imagine having electron structure that you try to understand in infinitely large atoms. Really what we're doing here. And we want to understand that the Madelung rule is actually a sort of true system for very large atoms, or whether it's kind of more like an empirical rule that works for the roughly 100 elements that exist in the system. So I need to go to a little bit more notation before we can start. So remember that psi with a C, sometimes the C will maybe be omitted, is always going to be a ground state for me. And I define the usual one particle density matrix. So that is an operator just on sort of on a one particle space. From L2 of R3 spin into itself. And the way you get it, so here I write down its integral kernel. And what you do, I actually forgot to overline here, or maybe it's just red. No, I don't think I can make that excuse. Well, actually, for atoms, I can always choose psi to be real, so it's not really a problem. But I meant to put a complex conjugation over here. So you take the product of the wave function with itself, and you essentially evaluate it on the diagonal, except that the first electron you put the x here and the y on the other copy of your wave function. And then you integrate along the diagonal in all the other variables, and then you normalize to, well, C or N, which is the same in our case. That's just a convention for normalization. And there's a tilde on the coordinates, because really this integration here, I want to do that both in the space variables and the spin variables. So really you should think of this x tilde as being both the space variable and the spin variable. And then when you integrate, you both sum over spins and integrate over the variables that you need to. And then you might argue that there's a sort of a shift of notation, whether you think of this as C2 or whether you think of it as all of that. So this is the a main object when you want to study many particle problems with two-body interactions, and you can understand the energy of wave function psi just in terms of the one. And especially when n becomes large, well then this psi becomes a somewhat unwieldy object, whereas this gamma here, well, that stays finite dimension, so you can hope to understand it. Then that's my first object. The second object is also standard. P with a little l here is the projection in the one particle space onto the subspace of angular momentum given by the index L. So that's also a very standard object, all kinds of yes, well, total depends what you mean, but total angular momentum, but not counting the spin. This independent, yeah. This operator here is oops. This operator is diagonal in spin. And what is our statement? Well, the statement is that if I take this gamma psi and then project it down to the angular momentum and take the trace, that is a measure of how many of the electrons have angular momentum. That's the distribution that I want to understand. I want to understand the angular momentum distribution of the electrons. That's exactly this trace. No. So L is the number. So it's positive integer, not negative integer. No, I mean, so depending on the shell, the L's that are available, that grows with them. So the higher the shell, the more different angular momentum. In the lowest shell, you have only L equal to 0. Next shell, you have both L equal to 1 and 0. But so this is somehow, I mean, we want to take very large atoms, so you could say that you're in some sense filling up almost infinitely many atoms. But then you want to understand how how many of these electrons are now filled in, say, an angular momentum 10, 100. And as this result will say, I mean, if you look at more clearly, I'm specifically not saying how many will have angular momentum 0. I actually also not really asking how many will have angular momentum. One, because the only thing that I can say something about is if I take the limit c to infinity to take a large atom, and then I scale my L with the power c to the 1/3. So I fix a number lambda, and then I think of L's that are like lambda times c to the 1/3. So really the very small angular momenta, unfortunately, I cannot really say something about in. Well, in some sense, lambda is the angular momentum divided by c to the 1/3. Right? So that's the meaning of lambda. Just to be precise, I mean, there's these funny brackets here. That means that I take this lambda times c to the 1/3, and then I round it up. I round it up. That's just, I mean, technicality. But that. So that's a kappa of lambda. You will see that soon. I mean, sorry, that's my notation for a kappa. And so what is? Let me just stress, what does this say? I mean, so we take the number of electrons of angular momentum L, and then we normalize it by the behavior, and the behavior goes with a 2 that comes from spin, really. Then there's 2L plus 1. You will recognize that as the number of different states that you could have with angular momentum L. And then there's the normalization C1/3. And then if you think of L as being of order C1/3, there's a C1/3 there. So it tells you that the sort of the size of this number here, that will be C2. So you have C electrons, and essentially for a given lambda, the number that you will have is C2. Okay, and times a coefficient that's given by this function kappa of lambda that has a semi-classical equation that I will give you in a minute. And just to be technical at this point, right? I mean, what we really prove, we prove this as the lower bound here is true pointwise for all lambda. The upper bound is almost every lambda with respect. So there's an integral involved. Yeah. Good. And just to stress this connection with chemistry, the Madelung rule that tells you how to fill in the electrons in different shells, you can do the calculation and see that that would give the same kind of behavior in the order of C, but it would give you a function which is actually, it's about to say linear, it's a straight line or a piece of straight line. It's an affine function. It's the positive part of the third root of 6 minus 2. That's what you would get from the Madelung rule. And that's, maybe you can read that it says different here in red. That is not what kappa of lambda is. So if you had really large atoms, then the Madelung rule. Yes, I think Jakob was a little bit first, even though Volker has preference. Well, that's a question. I mean, of course, but you cannot really prove it, right? And actually, even I should say up front that even within the periodic system, the chemists know that it doesn't hold for all elements. But it's sort of a way of filling in electrons, and the claim is that the few, there's like a handful maybe of elements in the periodic system where it fails, then the difference between the state that would be given by the Madelung rule and the true ground state energetically is very, very small. Well, of course, you can discuss that, but I don't think it's empirical in that sense. So I strongly believe that a chemist would say that it should hold with in non-relativistic. I mean, in this model as well. Yeah. No, it's on M. It's just on M. So you say if L is much smaller than C1/3, yes. It's kind of a sympathic because there's this Tietz potential that they claim. There's actually a different mean field potential than the ones we know that magically actually gives that for that mean field potential Madelung is exact. And of course, well, we cannot really compare that to any mean field model that we know. We would like to do that, but so I mean, of course, the theorem is what it is. It is possible. The answer to your question, yes, it is possible. But I don't. Thinking, I mean, the reason why I'm hesitating is that I wouldn't have any. I cannot think of any way of proving this. No, it's not good. That is true. I mean, so the limit of this function for lambda going to 0 and is not equal to this the third root of 6. So in that sense, I mean, it's wrong, but then again, the precision of this theorem doesn't go to that. So that's I should stress that Fermi, we all know from Thomas Fermi theory, actually we think there is a Fermi paper where he makes Thomas Fermi theory, but there's actually a sequence of 3 papers which is actually like really a 1, 2, 3, where the first one that maybe some of us know, there's the Thomas Fermi theory, but the others are maybe less read in our community. I can only recommend to read them. They're in Italian, but it's not very difficult to read, and they're very interesting. And actually, this problem is actually considered. I mean, it's almost 100 years ago, and Fermi, on the basis of Thomas Fermi theory, tried to understand how to fill in the electrons in an atom. I mean, that was before the Madelung rule was invented, and actually gets fairly close. I mean, in some sense, Fermi already in these papers writes down the equivalent of this kappa lambda, which I think, I mean, of course, then there's no mathematical proof that this is true in an interacting picture, but I think that is amazing. These papers are really incredibly interesting. So I can just recommend that, and I would even say it's even more fun because then. So let me just for maybe the few people in the audience who are not familiar with Thomas Fermi theory, let me tell you on one slide what Thomas Fermi theory is. So it's a way of understanding the energy of an atom in a very, very simple picture, where you just think of the electrons as having sort of a classical density, which is this function rho here, which you should think of as so it's a density on space, and the integral of the electron density should of course be the number of electrons, which we will take to be equal to a red C that is maybe invisible, because we want to look at a neutral matter. And then what do you do? Well, you mimic the kinetic energy of the electron density by the integral of rho to the 5/3. So there's a constant in front, and there's a long story about that, but somehow this integral of rho 5/3, that's what you would get from a simple classical. You had if you were filling just up states, then the kinetic energy of density rho would be like rho. So this is an approximation, but it's a reasonably good approximation. Then there's the interaction, the Coulomb interaction with the nucleus. Well, that's of course just the sort of the Coulomb interaction with the charged density rho, and then there's the electron-electron repulsion, which is mimicked by its classical expression of a charged gas interacting with itself through the Coulomb. So this is the Thomas Fermi energy functional as a function of density. And then, of course, you can define the Thomas Fermi energy for given n and for given z as the infimum of the functional over all appropriate densities. So the densities have to be negative. They have to be normalized to the number of electrons that you put in. And you want it to be in rho 5, in L5/3 in order for the kinetic energy. Once you have finiteness of this, then you can control the electron extraction by standard quantities. And it's known that if you are in the neutral case, which is where we are, then this functional has a unique minimum. There are many other interesting things that you can say about Thomas Fermi theory, and it becomes more challenging if you go beyond the neutral case. So different things can happen, but in the neutral case, there is a unique minimizer, and it satisfies the Thomas Fermi equation. And for that, let me write out the Thomas Fermi potential. So that's the screened Coulomb potential, if you want. It's the Coulomb potential minus the screening coming from the electron, the Coulomb interaction coming from the density. I have noticed that I have changed the sign or chosen the sign so that my Thomas Fermi potential here will be positive. It tends to 0 at infinity, but it is just positive. And then the Thomas Fermi equation is given in terms of this Thomas Fermi potential that the root, the 3/2 root of the potential is essentially the density up to some constant, which is of course related to the constant. So, and I should say that the constant up here depends on the fact that I have chosen the electrons to spins. If not, this constant will be different, and of course this constant. There's a very important scaling property that you can just look at the functional and see how it behaves on the scaling, and that then translates down into the following property for the potential itself. That if I take the potential at C, then it's the same thing as a scaled version of, say, the normalized Thomas Fermi potential, where the charge is just equal to 1. But where you scale with a factor of C to the 1/3 and then a C to the 4/3. So that means that if I have a large C, then this is a fixed function concentrated at distance C to the -1/3. And so therefore, for the few people in the audience who has known this for very many years, in some sense, a large atom is small. The Thomas Fermi theory describes correctly sort of the behavior of 90% of the electrons, fixed percentage of the electrons, and they will be localized at the scales, which is kind of funny the first time you hear about it. That really the larger the nuclear charge, but the smaller the atom is the bulk of the electrons. So that's everything about Thomas Fermi theory, or at least everything that I will need for the rest of my talk. Yeah. Okay. So what is this function kappa? In red, you might just be able to see it. I have just repeated what the definition, what the result in my theorem was, that this number of electrons of angular momentum L divided by the right power converges to a function kappa, and we want to understand this function kappa. I want to tell you what this function kappa is. And what is the definition? Well, it's 1/pi, and then it's an integral, and this integral is a one-dimensional radial integral of the Thomas Fermi potential, normalized, minus lambda squared, so that's the lambda, the parameter inside the kappa, divided by r squared. I take the positive part, and So I'm of course abusing notation in the sense that I will both think of phi as being a function of a three-dimensional variable, but it's actually a radial function. So I can also just think of it as a function of a positive variable. I will not change notation. And from this definition of kappa, I get a normalization condition, which is that if I multiply by 4 lambda and integrate up to infinity, then I get a 1. That's a consequence of the Thomas Fermi equation. If you take this integral and that integral and change them, do the lambda integral and use the Thomas Fermi equation, this. And what you should think of is that this is actually a consequence of the fact that if I sum over all L, then I count the number of electrons of angular momentum 0, 1, etc. That should give me all the electrons. That's C or N, if you want. That normalization and that normalization are related. But as we will see, since there was a lim-inf in my result, this normalization condition is really important because it means that in my lim-inf I haven't really lost it. It's the fact that here this normalization condition stays true after taking the limit, which might not be true. Good. And well, let me maybe at this point ask if there are any questions. If not, I will have to give the proof, which I'm very happy to do. But if there are any questions, this is a good time. Yes. Yes. I mean, of course, these are very different kinds of objects that take limits of, but yes, it's this thing that in mathematical analysis often we have a chance of understanding, crystallizing out a good behavior of the limit, but no, well, I will do that later in my proof, but in some sense I'm not. I mean, this projection here is really a kind of counting. But as I would maybe more talk about, say, biasymptotics. That would be maybe my point of view. But still, it's again this kind of counting or summing or getting information on moments of eigenvalues where the counting zeros moment. That is it's sort of a crucial thing in all kinds of spectral analysis. What is especially interesting in this case is that I have this interaction between the parts, and getting control of the interactions as well is part of what it's but as you will see, Volker did that work for us, so we don't. Okay, so let me give you the proof. I think I have 15 minutes left. That should be more than enough. Because actually, if you put things together in the right order, then this theorem is actually fairly straightforward. In some sense, what I will want to do is that I will want to make this into a question about energy. So that would be the sum of the eigenvalues instead of the number, simply because for that there are variational principles, and therefore that it's much more feasible to attack in particular in the interacting case. And then by standard arguments, you can often get around with kind of differentiating the energy in order to get information on number, and that is essentially what we do. So in order to do that, I put in a small chemical potential of equation mu, and I define the energy at lambda and mu, which is again sort of a semi-classical expression. There's a constant in front, and then there's again an integral of the Thomas Fermi potential minus this kind of angular momentum term and the chemical potential, and now it's to the power 3/2 instead of power 1/2. Again, the radial integral, and the n, so the number at lambda, angular momentum lambda, if you want, and chemical potential mu, that is then different constant, and then it's again the square root, and with the mu here. And this is defined so that this relation here is true. Well, it's defined so that this is the semi-classical expression for the energy, as you can see in the second. And then the number should be the derivative. So that's why why this constant is different from that constant. That's because this 3/2 come down and with a minus, so then it becomes the pi. And if I set the mu equal to 0, I get exactly the expression that I had for the kappa. Might not be able to remember that. That was on the previous slide, but it's true. The expression for kappa was to take mu equal to 0, then it is. Okay. And now just a couple of things, right? So the number is the derivative of the energy. The number is a positive function. So therefore, the energy is an increasing function of the chemical potential. The number is clearly a decreasing function of the chemical potential. So we have here that the energy is actually a concave function, derivative. Good. So now we need Volker. Actually, we don't really need Volker because we don't need that precision that he gets. We could do with something that is way weaker, which would then be actually enough to look at, let's say for example, Lieb's paper on Thomas Fermi theory and the Sieter-Weikart paper on the Scott. So what is stated here in the first fairly long series of inequalities? Now, is there anybody who cannot really read what's written in red here? Because now that's actually important. The red is readable. Okay, let me read it. So here, this is really the true quantum mechanical energy. I've written it as a scalar product, so I take the Hamiltonian, and then the scalar product or expectation value in the psi c, which was the ground state eigenfunction. So really, I could just here have written EC, namely the quantum mechanical energy. The statement is that true quantum mechanical energy is given very well by taking the mean field model where you use the Thomas Fermi potential as your mean field. So that is what I have written here. You take the Thomas Fermi potential. By definition, that was a positive potential, so therefore I put in a minus here. And then I take the corresponding Schrödinger operator. It's really a non-interacting picture. And I take the negative part of it and then the trace. I sum up all the negative eigenvalues of that operator. And by definition, my convention is that the negative part of a number is a negative number. And so here I'm summing a lot of negative eigenvalues, so I get a negative. This trace here is negative. And now in the Thomas Fermi equation, somehow there was an overcounting, right? Because I have taken the electron-electron interaction a bit too much. So therefore, I have to subtract the classical term here, which is just the integral of rho itself with the half and with the Coulomb. And here when I write rho, I really mean the rho Thomas Fermi C, so the minimizer of the Thomas Fermi, the one that went into defining the and what is known, I mean, this is really the same expression, sort of the same expression both on the left hand and on the right. On the right hand, I really have all the negative eigenvalues of this operator, and I know this is where, I mean, I use Sieter-Weikart, I get an error which is slightly better than c to the 2. Many of the people in the audience would know that this energy here goes like c to the 7/3. So this c to the 2 would be, well, 1 power of c 1/3 smaller than the leading order, and I need a slightly better precision for my for the lower bound, you can get an fairly easily an error which is even better, which is c to the 5/3, and you even have that you can write this not just as an estimate on energies, but really as kind of an operator inequality that you take the trace of the mean field operator, but in the one particle density matrix coming from the state. And again, there's this number which is so this is not the most precise energy information that we have about the atom. We essentially, for a neutral atom, know this up to the precision c to the 5/3, but I will not need that, and I cannot really improve my result using that. So this energy estimate is kind of all we need. Then if we use the fact that this Thomas Fermi potential is radial, then we can just sum over all angular momenta, both on this side, that side, and then what do we get? Well, we get that sort of subtracting. This is the same constant as that constant. If I take the full trace minus the full trace, notice here it's like the true sum of eigenvalues. Here it's the operator with expecting against the one particle density matrix. So this term minus that term is smaller than the error. That's what I've written down. But then I can use the fact that if I sum over all angular momentum, I of course get the identity, and this operator here is radial, so it commutes with angular momentum. And so therefore in red, I have written that it's true just to take the difference here of the full trace with the full trace, and I would get a difference which is better than c to 2. But I can also split that out into a sum over angular momenta. That's written in red here, sum over all L. And then I can project these individual terms down on angular momentum. I don't know that the gamma is radial or commutes with angular momentum. So therefore, I have to put up a PL on both sides. But this operator here, the mean field operator, but that commutes with angular momentum. So I only have to put PL on one side. And by definition, sort of this sum of negative eigenvalues, that's the sort of the lowest possible number that I can get. The gamma here would give you something higher. So if I look at this difference here of this trace, that trace, well, that's a positive number, and that's even a positive number for each individual L. So now here I have a sum of positive numbers that are better than c squared. So that means that each of these individual numbers are better than c squared. So that's of course typically very bad inequality. I have an infinite sum that is smaller than something, and then I say that means that each term is not smaller than that. It's a true inequality, but I'm probably losing. But as we will see, I'm not losing that much. And then I smuggle in, because I really want to do this differentiation right, I smuggle in a chemical potential. So just taking sort of the Lth term from this inequality and writing that out, I get that the angular momentum L contribution is larger than the angular momentum L contribution from the gamma, where I add a mu and then I subtract it again. Really just sort of adding and subtracting, of course, that's okay, up to this error of which is good. So let me tell you what the what the choice of going to the limit will be. So I need to fix again a little bit of notation. So really, I should speed up a little bit. So let me just say that fast. Given a lambda and a c, I choose the L to be lambda c 1/3, and then I round it up. So that's the L that I will be choosing, and then I will be taking a limit c to infinity, and then by this definition, for a fixed lambda, that will correspond to also taking L. And of course, this function here, L as a function of lambda, by definition is constant on intervals of length third, right? I've just rounded off. And so therefore, if I define pi lambda, pi of lambda of c in the ground state as being this projection that I want, with the 4 lambda at the bottom, then if I multiply up the 4 lambda and do an integral, then I'm really integrating, well, the lambdas go out. So I'm really integrating a piecewise constant function. So this is a Riemann sum. And it really becomes exactly the sum over all the PLs of the gamma psi. And there's a C1 minus 1 in. And what you cannot see, because I tried to be pedagogical, is that this sum, by definition, I round up, so I only get L from 1 to infinity. And I would need to get L from 0 to infinity to get the full number of electrons. So therefore, here I have an inequality that this sum is not equal to 1, because I missed the radial symmetric function, but it's smaller. And now we calculate. And essentially, this is the whole proof. We take some of the energy of the gamma psi projected on the angular momentum that we're looking at. Now, this is a radial symmetric operator. Okay, so first, by the variational principle, I can, instead of looking at this projection here, I can just take the true sum of the negative eigenvalues of this sum. That's the first. Two, projected on the right angle. So what is the dimension, right? I get a 2 from the spins. I get a 2LC plus 1 from the degeneracy of the angular momenta. And then I pass to radial coordinates, putting in the right power of R so that I really get it not on L2 of R squared, R plus, but on L2 of R plus. Then that makes it just a derivative here, and not standard version derivative. And then I scale by c to the 1/3. If I scale by c to the 1/3, then I get a power of c to the 4/3 out. And there's a c to the minus 2/3 in front of the derivatives. My mean field now becomes mean field normalized 1. And then I have the radial term here, and I still have the chemical potential where this c 4/3 has been. So that's just passing to radial coordinates and doing a scale. And now this is a fixed potential, essentially fixed, because the L sits here, but I can make a trivial bound from below, and then compare this to its semi-classical expression, because I have a small coefficient in front of the derivatives. So therefore, by just simple standard semi-classics, I get that this behaves like a phase space integral plus a small error. Okay, and picking up the powers are all in all. Okay. And now the energy that I defined was defined so that the semi-classical expression here is exactly the energy, the semi-classical energy that we had on the previous. Believe me on that, you just do the P integral and get the energy that we just and there's a 4 lambda c squared up. Okay, so this was a lower bound. There's of course a little bit of gymnastics with whether when you convert an L into a lambda, whether you exactly get an inequality in the right direction or whether you get some small errors, but it's clear that these small errors are small. So therefore, also for the upper bound, you can do kind of the same thing. But there's unfortunately again a pedagogical red spot here that I put in an epsilon because you need to change the L to something slightly bigger when you go the other direction, and therefore you easiest is to just have changed the lambda here by something small. Since we're doing leading orders in classics, we can let epsilon go to 0 at the end, and that will not. So we have changed, unfortunately, the lambda. So everything here has there's a c squared, there's a c squared error, and so if you take the upper bound and the lower bound and combine it with these expressions that we had, it's about. I will very soon be finished. We get this expression here that the semi-classical energy minus something that looks like the counting function with a mu is smaller than the energy, but this slightly changed. So this is true for all lambda, mu, and epsilon. And so we can this error. Oops, sorry. This error here is dependent on lambda, mu, and epsilon. So therefore, we can just make it disappear by taking the c limit first, and then we get that the counting function is this bigger than this difference quotient of the energies. And by taking the limit of all the parameters, we really get what we wanted, namely that the diminf of this counting function is bigger than the kappa. So, and the counting function was exactly what I wanted. So, wanted to prove, well, to get a liminf of. So this is really 1/2 of my statement, of my theorem. It's the lower bound, which is true 0.1 for any lambda. And then since time is up, let me just say that to get the other direction, I just need the normalization, which was still true for this kappa, that it integrates to 1, and then for 2 slur. So by passing the liminf under the integral sign by phi2, and the fact that phi2 becomes an identity, then I get the almost everywhere convergence free, since the integral of the limit is the same as the integral of the term in my limit. So that's all. Congratulations again.
There are any questions, Volker?
Sorry. I think our main goal really from the beginning was that we were kind of surprised that we could say something about individual angular momentum. Because the other sort of accumulative effect, as you say, well, that has been known longer, and it's maybe less surprising. In some sense, it's maybe kind of surprising that this normalization condition holds, right? And so therefore, this shows that we don't lose to leading order anything in this procedure. So yes, we could have done that, but that was really not what we wanted. No, I mean, this is in some sense not an easy theorem. I mean, this is a big theorem, and that's why, I mean, kind of stole it from Volker. Well, actually, this version we steal it from somewhere else into this position. But this is not just immediate, and you are right that in some sense that's why this lower bound is better, because in some sense the lower bound is easier in that sense. You have to control the correlations between the electrons, but there are the Oxford inequalities that do that for you in a very systematic way. So yes, I mean, maybe, I mean, so this is kind of the smallest possible number instead of this, which is one of the variational terms. So this term here is smaller than that, and in some sense that's why it's strong that it's on the right side of the inequality. So you're right to point that out, but it's part of what we know. We've known for years. I'm not really sure what monotonicity you're talking about, but I mean, of course, I expect this to be true point-wise, right? But point-wise, to what uniformity in the yeah, I don't know, and especially I mean your previous question, right? I mean for the small lambdas, which is maybe where we are really interested. Yeah, but no, so I'm not sure what to say.